Okay, so welcome to the official last day of lecture for not just this class, but also for this entire semester. So congratulations, you have not only survived physics, you have also survived the world's first America's first full semester of quarantine college. Last semester was sort of half one way, half the other, which was its own unique challenge, but we made it through this one. You guys have been great. It's been wonderful working with you. Still have the exam, but I'm not worried about anyone's grades particularly going into this. All you got to do is do it. And I believe in all of you. It has been, and is continuing to be, wonderful, and in spite of, again, the weirdness of the semester, I think you guys have made it as nice as it can be, given all of the nonsense we've had to deal with. So thank you all. I'm still new to teaching college specifically, but we've made it as good a start to my second year as we could have reasonably had. And that's well. I'm going to be getting to this point like closer to Christmas, so the spirit of the end of the year feels a little bit different, but not to underline what you guys have accomplished. You survived physics. You did it. You are still doing it. There's still one more thing, but it's not a thing that I think you guys should be worried about. Just show up, actually leave an answer for everything. I think everyone's going to be just fine. So, how is everyone doing? And are there any big pressing issues before I start talking towards you today? Specific questions or things you'd like us to discuss today? We need your one announcement actually. If you selected, like I say, that's so weird. If you selected the option to have a paper test hidden in an envelope that you open on camera, if you'd rather take the paper copy during the exam, those are in my office. You can come by and grab them right after this lecture. If you didn't select that option and aren't interested in that option, you can disregard that statement. But anyone have anything specific on their minds before we begin reviewing today? Okay. So, a couple of quality of life updates. Brightspace still has abandonment issues if I don't pay attention to it for long enough. Log in a new window, Brightspace. Okay, so on our exam of Brightspace page, so again, the final exam tab, we have the rules for the exam listed here, and then the topic list. It is a rather big column, but again, this is the same column as for the previous two tests combined, with a couple extra things on the bottom, just a few. Wait, did I write? You know what? I did miss something. So, brief glimpse into the back door. Okay, I forgot to list the additional electricity topics. That's my mistake. But, so, we have this nice big long list of every individual sub-thing that will be on the exam. It is the two previous lists combined, and just put in one single place for you, with the addition of a couple of the topics from last week added onto the bottom. We did talk about a lot of things last week, and so I'm focusing mostly on the things that I feel you should best know, just sort of the quickest, most useful factoids that we picked up from last week. focusing on things like the order of the electromagnetic spectrum and the visible light spectrum. The way I currently have them set up on this list, they're going from shortest frequency to longest in both of these, which also means they're going from longest wavelength to shortest wavelength. Because for a single wave type, the wavelength and frequency are inversely correlated. So, at least be familiar with this order. I think in previous years, a student pulled up a YouTube video with a song for how to remember this, but it's super cheesy and the singing's not great and I don't remember it. I'm not going to force you to listen to it, but if that's how you learn, there is a song for it that goes through them in this order: radio, micro, infrared light, UV, X-ray, gamma ray, basically increasingly danger level. And then the frequency, the order of light. This is the progression of light frequencies from shortest frequency to biggest frequency. It's Roy G. Biv. It's the order the rainbow goes in. The rainbow goes this way because of the frequency progression. And for electricity, be familiar especially with V equals IR, the statement that tells us all of the things going on in a circuit and how they interact with one another. Voltage pushes current through a resistor. Know those three things and know how they interact with this formula. Additionally, circuits use power. They use up energy in an amount of time. They do use up power. You can find the power required by a circuit by multiplying its current by its voltage. And lastly, the single thing that I hope becomes most applicable to you is how to calculate your electric bill. Brief review statement for that one. In the United States, and I assume other countries use a similar method, I just don't know what units they put them in. In the United States, you are billed so many cents per kilowatt hour. A kilowatt hour is a unit of energy because we're multiplying a unit of power by a unit of time. Power is joules per second, so if you multiply that by another unit of time, the times cancel and you're just left with energy. So kilowatt hours does tell you total energy that you used up. And 1 kilowatt hour is the amount of energy that a 1 kilowatt appliance will use if it's plugged in and turned on for 1 hour. The unit is exactly what it says right here. You multiply kilowatts times hours. Nice and straightforward for once. So let's say, for example, you have a 2 kilowatt, that's a really high voltage actually, sorry, that's a high wattage. So let's call this your air conditioner, because in a home, the single biggest thing, the single biggest drain on your electricity in any house, no matter what your parents tell you, complaining about how much time you spend on your Xbox or your laptop, is actually the air conditioning / heating. Because it's literally running basically all the time, and it has a very high power engine in order to do whatever it needs to do to the thermal energy to keep the temperature where you want it. The aircon is the aircon / heater. That combined machine definitely makes up most of your electric bill, followed closely by your refrigerator, and then probably your oven. So let's say that this is the wattage of your air conditioner, which is a lot. This is a very high wattage. And fun fact about your air conditioner, it's not running 100% of the time. If you can hear the air blowing, if you can hear the compressor making noise, it is on at that moment. But it tends to sort of go in bursts. When the temperature of your domicile reaches a certain threshold, like if it's too low for your setting or if it's too high for your setting, the system will kick on to correct the temperature, and then it'll kick off again until the temperature keeps resetting again. Which is why you're not always hearing the vent making noise. It does occasionally shut off and shut back on again, simply because if it was running all the time, it would eat up a lot more energy. use this method as a cost-saving measure. And your refrigerator does the same thing. Your refrigerator is just an air conditioner for one box. It uses the exact same technology. So let's say that in about a 24-hour period, the air conditioner machine is actually only pumping air for about 5 hours. Multiply 2 kilowatts by 5 hours, and that tells you that the air conditioner used 10 kilowatt hours of energy that day. It's that simple. Then you can use this conversion to figure out how many dollars that will cost you. Keep in mind, this is cents per kilowatt hour. This is the most recent Google result for cost of electricity in South Carolina. About 12.5 pennies per kilowatt hour. So if this was your air conditioner, this would only be costing you $12 a day. Okay, yeah, if this was your air conditioner, that would add up real fast. So this is probably too much wattage or too much runtime, or you've got the temperature of your domicile set to something wacky. This might be the cost of an industrial air conditioner, like one that's doing an entire power plant or something. Figures like this exist for bigger, high-energy buildings. But it's the same method for any appliance. If you know its wattage and you know how long it's turned on, you can find out how much it's costing you. And I'm going to go ahead and tell you, when your folks complain about, you got to turn the light off, you're running up the electric bill, your lights are the thing that takes up the least amount of power in your house. Leaving your lights on for 5 extra minutes might cost you an extra penny at the end of the month. Okay, maybe 30 pennies at the end of the month, but still.
What takes up the most?
The most is air conditioner / heater, followed by your fridge, followed by probably your oven, and then maybe your water heater. Please keep your food chilled properly, because that is what allows that's one of the things that lets modern society be possible, and it's why all of our meat doesn't have to be jerky. So, those are the additional things to focus on from last week. Oh, also, wave speed and frequency / wavelength, which ties back into understanding the ascending frequency order of the spectrum. To briefly glance at the rest of the list, conversions, metric scale, the fantastic 4 formulas.
Are scalars and vectors again?
Well, you need to know the difference. I might not ask you a scalar vector question, but there will be questions where direction is important.
Oh, it's just
I thought we had a chart.
The reason that this is listed here is not because there's going to be a question that asks you what is the difference, but understanding that the direction of a value is going to be important will play into parts of this assignment. Like in a collision, for example, you do need to keep track of what direction everything is moving in, because that affects what direction the total momentum is facing. And similarly with a projectile motion question, you've got acceleration down and horizontal movement at the same time. Those are separate dimensions, those are separate vectors. So this is more of a general listing and as for how it ties into everything else. Again, tying right back into vectors, one-dimensional and two-dimensional motion. A specific example of that is projectile motion. Did I go through this list with you guys already? I have too many lectures. Okay. Yeah, yesterday we did test 1. Force. There's lots of different types of forces: applied force, normal force, force of friction, force of gravity. Understand the differences and how they all function. Newton's laws, be able to tell them apart. Like on the last test, there's going to be a list of statements, and you're going to have to tell me of these statements which one is Newton's first law, which one is Newton's second law, which ones are not laws of motion at all. So So similar format to the last test. There's also going to be the same type of format for knowing the laws of thermodynamics. So again, recognize them, even if they're not written exactly the same way as you're familiar. For example, Newton's second law can be described as, you could just write the formula for Newton's second law, but you could also say that the net force applied to an object with mass will determine the net acceleration of that object. Because all of our physics equations are just the math equivalent of the verbal explanation. So this is the formula version for Newton's second law, but on the test, it'll probably be written out in words. So the laws might not always be written exactly the same way, so you're going to have to interpret the meaning of them. There's lots of different ways to describe the conservation of energy statement. That's the first law of thermodynamics. You can describe conservation of energy as saying energy cannot be created or destroyed. You can also describe it as saying the total amount of energy in a system is constant. They ultimately mean the same thing. So if you have any questions about any of them while you're studying, please let me know. Work and power. Work is energy used in a task. And remember the formula for work. These are the force in a direction, and then the object moves in that direction. Use energy to do the task. Power is work divided by time. It's the rate at which energy is used. Power shows up a lot because anytime energy is moving or being used as a function of time, you can describe that as power, which includes power getting used up in a circuit, energy traveling through a wall at a particular rate, that's thermal power. Power shows up a lot. There's a couple different formulas for it. Then energy itself. Originally we talked about kinetic and gravitational potential, understand the differences between them, and the fact that one tends to transfer into the other and vice versa as an object falls up and down. Momentum and impulse. This is mostly going to refer to collisions. So remember that in a collision, momentum is conserved. Momentum is an object's tendency to keep moving. If an object's momentum changes, it undergoes an impulse. Understand the difference between the two types of collisions. In all collisions, momentum is conserved, but in elastic collisions, kinetic energy is also conserved. Gravity. We've calculated gravity at least two different ways. First, there's Fg equals mg for weight of an object on Earth, but there's also the larger formula, universal law of gravitation, for your universal non-Earth-based needs. Be familiar with both of them. Rotational motion. Main things to focus on there. I'll pull up the exam formula sheet. Understand that these concepts, the angular counterparts to the first four formulas that we learned originally. These are the linear versions. These are the angular versions. Understand the differences between them, but also the similarities. And we have this list here that explains how to convert linear back into angular and vice versa. For the rotational questions on the exam, make sure you're able to, again, compare and contrast the commonalities and differences. Centripetal acceleration and force is sort of another bridge between rotational and linear because it's a linear force that makes things spin. There is a separate formula for it. Make sure you can distinguish between that and the other forms of acceleration and force on your formula sheet. Then torque. Torque is a force that makes things spin. There's only one formula of torque that you are going to need, and that is torque equals radius times force. Specifically remember that if you want to keep a seesaw balanced, a teeter-totter, the torque on one side needs to equal the torque on the other side. I didn't put that on the first test, so I'm not going to put it on the exam. And brings us to the divide between test 1 and test 2. Know the definitions of pressure and density. Pressure is force over area, density is mass divided by volume. The next couple entries are basically just the names of formulas. So I'm going to use this as an excuse to go ahead and look at our formula sheet. This is basically formula sheet for the first two tests combined end to end, but I've added labels explaining what each chapter was. And there's a third page with the two electrical formulas that you'll need, and also the two tables that were utilized in the thermodynamics chapter. So,
What's the number we supposed to remove before?
well, there's the specific heat of water, which is important. But you got that one there. The density, oh, also the density of water comes up pretty often. It is 1,000 kilograms per meter cubed. But if you need that for a question, it will be provided to you. Let me double, yeah. If you need that for a question, it will be provided to you. I didn't, yeah. And I give you density on a problem by problem basis. Scrolling up just a second though. These are the first couple of formulas there that we learned in chapter 5. Definition of density, definition of pressure. Then we have how to find pressure at a depth in a fluid. So this is pressure at some depth h into a fluid of density rho. Then the buoyant force. Keep in mind that this is the force that the fluid exerts on the object that is floating. So the density is of the fluid. That's a lowercase b. There are some slight differences here between how I write things and how the computer spat out the formulas. And then we have Pascal's principle, which refers to the example where a pipe system has a narrow pipe on one side and a wider pipe on the other. As the area changes, the force applied to one side will be different to that of the other side. Like, again, the system they use in car shops. Then, moving into chapter 6 territory, you've got the continuity equation. As you change the area of a pipe, it will also affect the speed that fluids move through it. Typically, as the pipe gets narrower, the speed goes up. And everyone's favorite, Bernoulli's equation. It will be present, but do remember that the questions where this shows up are designed to be the ones that, I don't write them to trick you, but these are the ones that are worth more points than they otherwise would be, because to sort of add in the bonus points that get factored into the whole thing. So, the thing that will get you, at least the thing that will get you the points that will get you a 100 out of 100. The thing to remember here is recognize what type of problem needs this equation, namely a system where you've got a problem that involves a shift from sort of one part of a pressure system to a different part of a pressure system. Like you've got a tank of water that springs a leak and you're comparing what's going on inside the tank to what's happening outside of the tank. As long as it's a Bernoulli's question and you write down this formula, you get most of your points. And then you start getting even more points as you start canceling out the things that you don't need. Because the trick with this formula is, I'm never going to give you a question where you need every single piece of it. There's always going to be at least one thing, probably two things on each side that cancels out just because it's equal to 0 on that side, or because it's the same as on the other side.
Hey, I'm sorry. So G is that's good.
Yeah, lowercase g is always 9.8. No one reuses lowercase g.
That's the height, right?
Yes, that is the height.
And then P is the pressure. No, P is the density.
Little rho is density. So if These little ones are density. They're smaller, they're slanted slightly, and they're rounded at the top. The angular uppercase P's are the pressure, like the innate pressure applied to that side of the system.
And W, like the big W outside of the formula that work, and then inside of that Y.
You got that one first. If the unit is W and it's attached to a number, it's watts. If the W is in a formula, it's work.
And they got to find
To my knowledge, there's only one letter that's used across the board as the same thing for the variable and the unit, and that's volts. So again, recognize what types of questions need this. If you just write this formula in, you get most of your points, and you'll be just fine. The bonus points come from the steps after that. That's, again, there's 210 points, graded out of 200 of them. You get bonus points, you can get higher than 100. It's the exact same way the tests work. Thermal energy is a additional energy type. It is a form of energy like kinetic or gravitational potential. Thermal equilibrium is a state where objects are at the same temperature. That does not mean that they have the same amount of thermal energy in them. Thermal energy is dispersed over an object's entire mass. So if it has more mass, it needs more thermal energy to be at the same temperature. The example that I was taught very frequently is if you have 1,000,000 cups of coffee that are the same temperature as 1 cup of coffee, there's more thermal energy in the million even if they're at the same temperature. Thermal equilibrium just means same temperature. It means that thermal energy will not transfer from one to the other. They're balanced. Speaking of transferring thermal energy, there's 3 different ways that you can do that. Conduction is through touch. We have a specific formula later on that summarizes that. There we go, rate of thermal conduction. You also have convection, which is through a fluid like boiling water or the air in your stove. And then radiation, which is the thing the sun does, and heat lamps, and also these light bulbs. Just remember the differences between them, and radiation does also tie into light and such. Fire is a complex bag because it's kind of doing all 3 at once.
I don't know, like it's good to deal with radiation.
One more time.
Like it's really to teach us about radiation. We used to like classify that as radiation.
Well, humans have been struggling to grasp fire since literally the beginning because you can see it, but it doesn't have physical presence. Like if you try to touch it, it's not solid, but it still hurts you. You can see it, it makes things warm. What is it? Like, how do you contain it? Fire is technically a chemical reaction that gives off thermal energy and light. So it's not actually an object, it's a process. And because it gives off thermal energy, it can give off energy through conduction if you are touching the things burning. It can give off thermal energy through convection because air needs to be present to have fire, and the heat and smoke is naturally going to rise because of that, which is why you always put whatever you're cooking over the fire instead of under it. And it gives off heat through radiation because it makes light. So fire's a triple combo. Know how to convert between temperature scales. We have Fahrenheit, Celsius, and Kelvin. Also remember that we have degrees Fahrenheit, degrees Celsius, but just Kelvin. I don't know why Lord Kelvin decided that. Then the specific heat formula, as you add thermal energy to some mass of some material, its temperature will change. We have a table that will tell you the specific heat of different materials. The laws of thermodynamics, there are 4 of them. Be able to recognize them in a list and number them accordingly. Like on the last test, there will be 6 different statements. You need to tell me which 4 of them are the laws of thermodynamics. Of those laws, we have conservation of energy from the first law. You add thermal energy to something and it does some amount of work. The remainder will be thermal energy trapped inside of the object after the fact. And in general, if something gains thermal energy, something else had to lose the same amount because it always existed. It's just swapping objects. What you're going to need to remember for entropy is mainly just its definition for the sake of remembering the second and third laws of thermodynamics. So as long as you can recognize, interpret the meaning of the second and third laws of thermodynamics, that will cover everything you will need for your knowledge of entropy. Just what factors into those definitions. Thermal efficiency, simply the output over the input of a machine. 100% efficiency is called perpetual motion, and it is a pipe dream because as long as friction exists, we can't have that. Most machines have an efficiency of about 20% if you're lucky. This includes your own body. Rate of thermal conduction, that is one machine. This formula, and the K constant represents the material that you are conducting through. We have a nice table for that. And that is, we already mentioned things at the end of the list, all of the different topics that will be present. It is admittedly a lot of different things, but they are all very interconnected, and as such, one question might ask you about multiple different things. Within the thermal energy questions, there might be something that asks you about what is the rate of thermal energy traveling through this object, and then once the thermal energy is on the other side, what will the temperature change be because that thermal energy is now in some other object. They are combined in a way to try to make them as coherent and sequential as possible. Rather than asking you a million questions about each individual one, it's 18 questions, a lot of them connected in ways that make sense. Because if you had a million questions to do, you'd be here all day. And if I had a million questions to grade, I would go even more cuckoo bonkers than I already am. So that is all of the individual things to study. But you guys you've been reviewing in class all week, and I know you guys have been studying on your own, which is wonderful. And other documents listed here in the tab. The formula sheet is here, but one will be provided to you. If you are taking it in person or if you're getting an envelope from me, you'll be handed a physical formula sheet to guarantee that you'll have one. And if you are taking it online, I will be sending you a copy of the formula sheet in the same email as your exam. So you will have access to it. It will be at your fingertips. The formula sheet is your friend. You will have access to it. You will not. It is against the rules to access your notes or the internet or people. You do have me though. Please ask me questions. The worst I can do if you ask me a question is just be silent. I will typically try to point you in the right direction. And do remember, officially, I cannot tell you if you got the right answer, but if you get the right answer, it does make me happy, and I smile when I'm happy. So, nonverbal communication. Excuse me. Formula sheet is here though, if you would like to review it during your studying. We also have the answer keys to the 2 tests and the practice questions. The answer key for the practice questions will be going up shortly. I was working on it last night, I hit a stumbling block. While I've got your attention, and while I've got this pulled up, if you've been working these questions, or if you plan on working these questions, we have a collisions question here. This is an example of momentum conserved in a collision. And I'd ask you to work it two ways. Once if the collision is inelastic and once if it is elastic. The inelastic version is quick and logical and makes sense. Unfortunately, the way I set the question up, the elastic version takes way too long to work. And after I made several mistakes finding the answer myself, I kind of hit a wall and had to go eat dinner, and then the rest of my evening started. So, if you are doing these questions, I'm going to go ahead and tell you, don't sweat over this part. It's not, for the sake of the exam, working this specific collision as an elastic collision is not going to actually benefit you because it's going to take way too long. You're not going to get any benefit out of it. And it's entirely because of how I set the question up. There was a mistake in my writing that made it harder than I was intending to work it as an elastic collision. So if you are working these or looking at my answer key, it's a problem with how I wrote this one. The inelastic one works great. Inelastic is nice and straightforward and good. It's only a problem with how I wrote the elastic version. So just brief declaration of that before you work, if you haven't worked it yet, and before you look at the answer key for it. But the key will be up today. We're going to finish it over lunch and scan it and then upload it before the weekend starts. And that's really it in terms of what's going to be there. And I've been looking at your grades, and I honestly think you guys are going to be fine. If you as an individual need or want information about what your grade is, what you need to do on the exam to pass the class or get a specific final average, I can find that out for you and share with you how I got it. But after working with you and looking at your grades, I don't think anyone is in any danger here. Because as long as you the exam and leave nothing blank, looking at the math, I'm telling you this to assure you not to worry. You still have to do it, you should do your best, but no one's future's on the line here. You guys have done great. I'm proud of you. You're all going to move on to wonderful things, and I can't wait to see what they are. Including a nice vacation. Boy, howdy, do we all need it.
Thanks. You doing this vacation?
I'm missing you guys. Yeah. It's always bittersweet when a semester ends. Okay. Anything you guys need at all in terms of questions about the exam, what you need, questions about specific things? I know we have a lot of people asking for Louis' help. Don't have any right now, that's fine. It's Friday, and you guys have lots of things on your plates to deal with. If you couldn't get food, please go put something on your plate. If you have any questions at any time, please let me know. If you still need to collect a tested envelope, also sit by me and let me know. I'm in my office shortly. They are in my office, and you can head over there. But if you have nothing at the moment, I'm going to head out. I do hope you all have a wonderful day and wonderful studying on your, I know you have multiple exams, not just mine. So good luck to you all on all of them. And thank you.
You made it to the last day.
I don't need your calculation.
That's freaking
Your homework, and your lab average as far as I've calculated is also an A.
So, is it, do you guys have A plus minimums?
I do give
I'm chewing this gum.
My policy is I give pluses, I don't give minuses.
More.
Okay.
I give pluses where I can, but I don't penalize for minuses.
Alright. Wait, you
Well,
have my grade as well?
yes. Is that what everyone's waiting on?
The finals.
Okay.
Fine.
Yes.
You waiting on blood?
Let's see.
I wanna know what my new grade is. You good enough? See, you think little. You think too little.
Tell me.
You gotta think above and beyond.
We tell me if I got 80%, I'm still in the high school.
Nah, bro, you make it better, then we got to be.
Welcome to college, you're actually doing
I can
fine.
use this, I can use this class as experience.
Yes.
This class is
Bro.
Last name again?
It's a lot.
Tested.
I'm not good at math and science. Good at English and
B
business.
lab average, so
Sorry about that.
without having to pull out my
Yeah,
calculator.
No, I can write a paper like this.
Especially-
I can
We
do
test that.
calculations. I just said no.
I can write this. It might not be the best, but it'll be good. On, cause you put in a butter bread, I don't know.
Oh,
Oh, so you, oh,
is
so
that-
Just cause you got to put it on that.
Yeah, before I calculate anything else, the lab average adds up to an A, rounds up to an
Slam
A,
this
so.
thing, right? It's probably worth it.
can I get a sum for 2 one more time?
Correct.
Yes.
Yes.
Just tell me it's higher
Hey,
than
bro, you got a bullet hole in your
I don't know if
sleeve, man,
it's-
flu shot you.
It'll probably average to about the same, just
That's
before,
hot slipper.
before pulling out my calculator to check myself. Yeah, it's probably averaged out somewhere, right?
Huh?
You basically saying it's not smart.
Everyone's smart, you were all done well in physics. Well, this is physics, and you guys have done it,
I'm so
right?
tired.
There's only one last obstacle.
Asking who helps him with his work every time he over there like this.
Oh, look, getting help, it is important to know when you need help, and honestly, having it explained to you